Marc Artola, ESR number 10, based at Imperial College, and working under the supervision of Andy Wynn and Rafa Palacios. So today I will present you what has been the main focus of my research and of my thesis, which has been trying to find the minimal or like the simplest models of highly flexible aircraft appropriate for control. That is simple in the sense of having the least possible number of degrees of freedom, but that they should still capture the main nonlinear physics of the systems. So I will start my presentation with a brief research motivation. I will follow by introducing what we consider our ground truth simulations or our ground truth model, which we will use as a reference to compare the simulations of our internal models, and also we will use it as our controlled plans. Then I will present you, or I will show you how we construct those internal models for control, which are the control and estimation strategies that we use. And I will end up with showing you some relevant numerical examples. Also, we'll give some concluding remarks on our research, and also a brief summary of my ConFlex fellowship. Okay, so next generation aircraft, and especially high altitude long endurance aircraft, or high altitude pseudo satellite concepts, are striving to improve aerodynamic efficiency, since they aim to remain airborne almost perpetually. So that is done by using every time slender wings, and using lightweight composite materials, which has an immediate effect that the flexibility of these airframes is increased. So large deformations can be expected, which necessitates of these geometrically nonlinear models. Also, when traditional control methods have been applied to these structures, they have been shown to be very vulnerable still to atmospheric disturbances or turbulence. So this has highlighted the need of advanced or novel control strategies. So here I introduce what I said we consider our ground truth simulations. For that purpose, we use SharpEye, which is Imperial College's Nonlinear Aeroelasticity open source software. It basically solves for a finite element implementation of this traditional displacement-based geometrically exact formulation, which is a second order in time system with very high or very strong nonlinearities, which solves for the flexible degrees of freedom, which are coupled to the velocities, to the rigid velocities of the structure. So this structural model is tightly coupled to an unsteady vortex lattice formulation. So the unsteady vortex lattice method solves the potential flow equations by discretizing the main lifting surfaces, such as wings, and also the wake that it generates into small discrete panels. And each of these panels has associated circulation. So these circulations we denote here with gamma. This is what forms the state space of the formulation, together with the coordinates of the wake. This wake follows just a simple convection following the induced local velocities. As an input of this system, we have the coordinates and the kinematics, that is the velocities of the nodes of each of the panels of the wing. And that can include elastic deformations, rigid body dynamics, or other like control surface deflections, for example, or gust external velocities. And as our outputs of the system, we have the aerodynamic forces, which are split into unsteady and steady contributions. So one thing to note is that these intensities are obtained by solving the non-penetration boundary conditions along the main wing, which is the main source of nonlinearity, since the solution of the UVLM depends on the instantaneous configuration and velocity of the structure. So for our internal models for control, we have to turn to an equivalent description of geometrically nonlinear beams. That is, we turn to one description that is very compact and has a neat structure, which allows, importantly, for efficient low-order nonlinear reduction methods. So by the choice of velocities and strains as a main variables, we can describe the dynamics of these structures by using first order, both in time and space derivatives, and also with nonlinearities, which are up to quadratic terms. So here is how we construct finite dimensional low order models. For that, what we do is we compute the linear normal modes of the structure, which are the eigenvectors of the linearized equations around the origin. For our solution, we use these ansatz. So we assume that we can build approximations of our solution using these eigenfunctions multiplied by some temporal coefficients. And by a Galerkin projection, we finally obtain this low order ODE, ordinary differential equation, in terms of the temporal coefficients, where we see that the nonlinearities inherent in the systems are retained. So for the aerodynamics, we saw that the UVLM is naturally nonlinear. So what we do is we linearize it around the frozen geometry and of the structure and of the wake. And with that, we can express this linearized system in using a discrete time linear time invariant system, using this perturbation linear variables around that reference configuration. So by using that, we can project the outputs and inputs of this UVLM formulation. So we saw that these inputs and outputs were linked to the nodes of the panels, but just using some mappings between these the geometry of the panels and the beam center line, we can relate them to our structural variables, and then we further project them using our modes, our truncated basis. So that reduces substantially the input-output dimensionality. That is the number of transfer functions, and for that we can make use of efficient interpolation, reduced order modeling methods. So finally, these internal models will underpin nonlinear model moving horizon estimator and model predictive control strategies. They are similar in the sense that they account for fully nonlinear dynamics, and they also can handle directly input and state constraints. And here we show in this schematic picture how we construct our closed MPC loop. So we have here SharpEye module, which is this elasticity simulation host, which we use here as our controlled plant, from which we take measurements at defined sampling points in time. So these measurements and the past history of measurements is fed to the moving horizon estimator, which provides us with an estimate of the current state of the system, of our internal model, and also the past disturbances. These two variables are then fed to the MPC block, which by solving this optimal control problem is able to produce some optimal control law, which is fed back to SharpEye, and then hence the loop is closed. So we now show some numerical examples. So for this first numerical example, we consider the fuzzy wing, which is a very flexible clamped wing test case, which is actually built at University of Technion and has used, to benchmark nonlinear aeroelasticity simulations. In our case, we take a simplified model, a simplified computational model. And importantly, this wing has compelling flutter properties. So this can be seen here. What we have in this graph is, in the vertical axis, the velocity of the wing, and in the horizontal axis, the normalized wingtip displacement. So we see that we are going highly nonlinear. There are deflections here, consider deflections of even 50 or 60% of the span. So the way this graph works is we take the wing, we put it in a wind velocity, in a fixed wing velocity, and at a certain angle of attack, so that wing deforms, reaches a static solution, and around that static solution, we perform linear analysis, which reveal if the system is unstable or stable. By doing that, we can identify these two large red regions, which are regions where this flutter instability occurs. And what we do is we set up the problem, this first test case problem, using a velocity of 50 meters per second and an angle of attack of 4 degrees, which initially we see that this point would sit here inside the red region, and hence flutter will appear. So in these two plots, the first one, we show here the wingtip displacement against time. The second one, we show the flap deflection against time for the closed loop problems. But we first take a look at the open loop. We see that when the wing is released, the wing starts to deform. And when it starts to reach the static equilibrium point, we see that there is this onset of flutter, and some oscillations start to grow and then so we set up our MPC problem to suppress those oscillations. And what we see is that when the MPC horizon is that we use are shorter, the typical direct actuation mechanism is obtained here in blue, where the flap is deflected synchronously to the flutter oscillations. And this achieves a substantial reduction in the amplitude of these oscillations. However, when we increase the horizons of these MPC problems, we see that the controller finds an alternative minimum, which consists of a smooth deflection of the aileron, which basically brings the wing to a more deformed state, where it knows that a flutter no longer occurs. So this is quite remarkable, because it basically highlights the controller knowledge of the nonlinear stability properties of the wing. So that's going back to this plot. The controller is trying to bring this point, which was initially sitting in this red region, outside to the right in this white region, by deforming, by bringing the structure to a more deformed configuration, where flutter does no longer occur. So for this second case, we consider a free-flying aircraft scenario, where we use this high-altitude, long endurance concept with a weight of slightly less than 80 kilograms, a very high aspect ratio, and typical flight velocities of 10 to 15 meters per second. So the control inputs that this aircraft has is one propeller, which gives us the thrust command, which the thrust is sitting here on the intersection of the wing and the fuselage. And then there is a T-tail tailplane, where there is a rudder and a null-moving elevator. So from the overall weight of the structure, 50 kilograms is a concentrated mass, which is sitting here at the intersection as well. So this is considered to be a model of the payload of the system. So this control problem, what we try to do is to stabilize the aircraft after 50% of the payload is dropped just after starting the simulation. What we show here are the open loop results. We show the angle of attack, the pitch in the red and yellow or brown respectively, and also the flight velocity. So we see that after the payload is released, there is a sudden decrease in angle of attack. That's because of the sudden vertical acceleration of the aircraft, which reduces the effective angle of attack. And then we see that the aircraft is left in this nose-up climbing trajectory with an increasing pitch, and also a reduce in flight velocity. Most importantly, we compare here our reference results in solid thick lines against our internal models, and we see that for longer enough horizons, our internal controllers are able to reproduce quite accurately the dynamics. So then we employ this internal model to underpin our MPC and MHC strategies. And we see that the results that we obtained are quite successful. We see that the aircraft is stabilized after a very reasonable 5 seconds. And also here we show again the angle of attack, pitch against time. But here we also see the normalized inputs that the MPC produces, and also the estimation of the lost mass, which is estimated directly by the estimator. So these are also quite important results, because it highlights the capability of the internal models of handling changes in the nonlinear equilibrium points, just because after the mass is released, the inertia distribution is changed, so the equilibrium point of the structure changes. So both controller and estimator are able to perform quite well despite of this sudden change. And well, finally, this was something that we decided to give a try, to explore after some insightful discussions with Professor Thuathua at my secondment PAU. So we decided to give it a go to machine learning. So for that, what we do is we decided to substitute some of the blocks of our internal models by some data-driven model fitting. So these models can be shown here like quite schematically. So y would be the output, x would be the inputs, and beta are the coefficients of this data-driven model, and this theta of x would be a library of different functions of the inputs that we can choose freely. So so these data-driven improvements are targeted to improve some observed or some identified shortcomings of our model. So one of them is the gravitational model. Since we use the intrinsic equations, the rotations are not part of the main variables. So if we wanted to model gravity, we have to augment our internal state space by including an approximation of the rotations, and that increases the size of the systems quite substantially. So by turning to data-driven, we want to find an expression of this gravitational forcing, directly linking it to our intrinsic variables, namely the deformation state. For the aerodynamic model, we have identified that the linear reduced order models are unable to correctly predict forces, especially induced drag, and also the linearized formulation is transparent to variations in the dynamic pressure. So what we do is we solve a lasso regression problem, which for some snapshots of inputs and outputs, we can find these coefficients beta of our models by solving this least squares minimization problem, which is regularized by this L1 penalty term. And for that, we use quadratic models. So we select this library to have monomials of up to second order in all of its inputs. That's done for consistency, just to match the complexity of our of the original models, which are only which have only quadratic nonlinearities, and also it facilitates analytical manipulation and the derivation of the sensitivity equations. And also, and most importantly, for example, for the aerodynamic model, we expect these quadratic approximations to capture both the induced drag and the variation, the sensitivity to variation in dynamic pressure, since they are both second order effects. And also, this approach can be slightly modified to include some constraints on the physics. So for example, we can impose the trim conditions of our data-driven models, and also ensure that the models that we obtain a posteriori are stable. That can be done, for example, by constraining the quadratic terms to be energy preserving, then like solving or checking some conditions a posteriori, we can ensure that the dynamical system that we obtain is globally bounded. So then these data-driven blocks are substituted in our internal models, and we do a first open loop comparison with our reference results in SharpEye. So this is for the previous payload drop case, where we have in fixed solid line our reference solutions using SharpEye, and here in thin solid lines we see the internal models that when are integrated long enough, we see that they show this divergence, and they end up blowing up. But yeah, so what we see is that the data-driven additions, they improve the accuracy of the models, and most importantly, they avoid this blow up of these solutions. That has been checked also with some other cases where we see again that this dashed dot line, which is the one with the data-driven additions, reduces the discrepancies, which are very high and very noticeable of our linear-based aerodynamics model. I mean, we still observe that there is some discrepancy, but we believe that this is caused by the modal truncation. So remember that at some point we decided to truncate our solution, our ansatz for the solution. We have also tried to see what the effect of these data-driven improvements is on the MPC MHE closed loop performance. And we have seen that the estimation problems are highly improved due to this improving in internal model accuracy. But we still have some inconclusive effects on the control problems. So yeah, so this is some a summary, a bit of what I've been showing up to now. So with this framework, I've shown you that we can build nonlinear low-order internal models for control. These are very concise in size. For example, this last example where we have included the data-driven improvements, we can model these high-altitude, long-endurance aircraft just by using 30 states in total. Then we have shown, the potential of data-driven strategies to improve the accuracy of these internal models, and also in these application examples, we've shown how these control methods explore clearly nonlinear control mechanisms, which is quite novel. And this makes us believe that the framework opens the door to real-time control of very flexible aircraft, because the simulations that run internally using these very low-order models can be done in real time, like with specialized software. And well, I'd like to end up the talk with a brief summary of the ConFlex Fellowship. So the publications which have been already published, it's been 3 journal papers and 4 conference papers. And as Charlotte mentioned yesterday, we got recently accepted a paper in common with her, so that was out of the collaboration at Erlangen. And yes, this I already mentioned it yesterday as well. I only managed to submit the thesis yesterday, and then I'm awaiting for a date for the defense. And I mean, I will start to apply to, well, I have applied to several research and development engineering positions in the industry. So that's where I would see myself in the near future, I hope. So yeah, this is the end of the presentation. Thank you.
Thank you very much. So, are there questions or comments?
If I may start, I have a question, Marc. Thank you.